Okay, today we are looking at electrolysis, which is our very last lecture for a full unit. Our next two lectures are just like an organic overview, so this is literally the last lecture, full lecture of the school year of AP Chemistry. And if you're not taking organic, it's probably the last lecture of your high school chemistry career. Don't cry. It'll be okay. Should be. Should be sad. You don't know what you've got till it's gone. Just saying. All right, so electrolysis, electrolytic cells. I'm going to let you read through these notes because in the process of teaching you the stuff, I will hit everything on this sheet. But long and short of it, these are non-spontaneous cells. The purpose of electrolytic cells is mainly for the production of stuff. We can produce gases from electrolytic cells that can be isolated. We can plate things. We can produce solid, really reactive metals like sodium. Apparently Rui is obsessed with sodium. He wants to produce it so he can make rockets go. Anyway, so that is what we use electrolysis for. And because they're non-spontaneous, we need a power source. Yes? Yes. In the future, just get up and ask. Just leave. Go like this. Didn't require any. There you go. That's good. Okay, so let's go ahead and jump into talking about electrolysis itself. Because we live in a world where water plays such a huge part and most of the stuff we deal with is in solution, part of being successful with this is knowing what happens when water is electrolyzed. Okay? So in the process of electrolysis, something is oxidized and something is reduced. When we electrolyze water, water itself can both be oxidized and reduced. So what you guys need to know to be able to do is how to write half reactions for the reduction and oxidation of water. So I have a few things that will help you understand here. Put the phone up. And by up, I mean away, not just on your desk. When water is oxidized, we produce oxygen. It's an easy way to remember it, and I'll show you why. Oxidized, we produce oxygen. Why is it oxidized? What's oxidation state in water? -2. What is it in oxygen gas? 0. That went up in charge. That's oxidation. Okay? When water is reduced, then we produce the other gas, H2. So H2 went from +1 to 0, and that is reduction. Okay? Now, in order to get fully balanced equations, remember when we do the half reactions, it could be an acidic or basic. Because water has the properties of both, one of these is going to be acidic and one is going to be basic. So we can go ahead and say water then, when it's oxidized, it's acidic. And where does oxidation occur in a cell? Anode or cathode? The anode. So notice all of these starts with a vowel. Isn't that convenient? Reduction then will be the basic one. And where does it occur? The cathode. So there we go. So because the oxidation half reaction is the acidic one, it's going to end with an H+. And this is the basic one, so we're going to add an OH-. That's the reaction. At one point when we do some electrolysis and Faraday's calculations, you'll need to have this balance. So let's just go ahead and balance it real quick. I've got 2 oxygens. I need 2 oxygens. That gives me 4 hydrogens. How do I balance charge? How many? 4 electrons. So that is the balanced oxidation half reaction. All right, reduction. Reduction is the basic one at the cathode. To balance this, it just helps to mentally think of this as HOH and balance the H's with this and the OH's with that. So I would need 2 H's then, and then I'd need 2 OH's. Then how do I electrically balance this? 2E on the left. Good. So those are my 2 half reactions for water. Don't stress about these. You can kind of rationalize through them, but the main goal will be when water is present in an electrolytic cell, it may be oxidized, it may be reduced, both may happen depending upon the situation. So let's talk about an electrolytic cell and the parts. And the first thing we're going to do is just draw it electrolyzing water. So our electrolytic cells are 1 vat cells, okay? And this time we have 2 electrodes submerged in whatever we're electrolyzing. So in this case, we're electrolyzing just water. The electrodes themselves are not part of the redox equations like they were in voltaic cells. They're merely surfaces for things to either be plated on or we can produce gases at these. They are not an active part of the redox equations, okay? So if we were plating jewelry, you would literally put the piece of jewelry in the solution and it would be plated, okay, because it itself is not a part of the reaction. So a little bit different about this is instead of just the wire, we have to have a power supply. So the big indicator on the AP of what kind of problem it is, they'll sometimes have literally the word power supply written on that. So when you see a power supply, you know it has to be an electrolytic cell because this is non-spontaneous, so we need something to make it go. So the translation of the positive and minus, if you attach it to the positive, this is positive. If you attach it to the negative, that then is the negative. But the bad news is that the positive now is the anode and the negative is the cathode, which sucks. But it's not a big deal. That's literally the only difference. Oxidation still occurs here. Reduction still occurs here. Okay? So that sign is really the only difference. Electrons still flow the same. How do electrons flow? Anode to cathode. So our electrons flow from anode to cathode. All right? So if I ask you the question, what gas is produced at the cathode in the electrolysis of water, what would you say? H2. Because reduction occurs here, and we know that reduction of water is H2, and that is basic. And we know that oxidation occurs here, and we know that's oxygen, and it's acidic. So what goes on physically, we have at this hydrogen gas coming off of this puppy, and these OH minuses kind of float around, hanging out near the electrode. All right? And then on this electrode, we have oxygen gas being produced, and we have little H pluses hanging out. So if any of you want to try this at home, I'll give you a little bit of phenolphthalein. If you want to get a dish or a cup of water, use some pencil leads, 9-volt battery, attach it with some wires, you can electrolyze water. And if you put phenolphthalein in the water, right here by the electrode that's producing the hydrogen, by the cathode, what does phenolphthalein do in basic solutions? It turns pink. So you would get like a little pink production hovering around that electrode. So you can try that. If you want it, I'll give you a little Burrell pipette with some sodium, some phenolphthalein in it. I won't give you any sodium, Ruri. Sorry. I know you want some, but you can't have it. All right. So this is the electrolysis of water. They really don't focus a heck of a lot on the drawing of this. What they focus on is what is produced. And then you'll see in these Faraday calculations how long it would take to produce a certain amount, what amps would we need, that kind of thing. And yeah, we're going a little bit into physics today. I'm sorry. It's not my jam, but we'll do it. All right. So now we're going to talk a little bit about the concept of electrolyzing other things. But let me go back to this slide and just talk a little bit. So I need you now to have an open mind and to roll with my metaphor. It doesn't necessarily make 100% sense, but it works, okay? So those of you who had me last year, you've heard all of this already, but it's good for you to hear it again. When I think about the electrons and I think about them running through, I think about thousands and thousands of little yipping chihuahuas, okay? So I want you to think about these electrons as little chihuahuas. We've got reduction chihuahuas and we've got oxidation chihuahuas, okay? And they have to eat. What they eat depends on what they're provided with. Here, we just have water. Water can be both reduced and oxidized. So both the reduction and oxidation chihuahuas are just attacking, no problem, right? Well, the chihuahuas, you can see them up there, aren't afraid of that water. Look how cute the water is. Isn't he adorable? He's like, hey, it's a little water drop. The chihuahua, however, is afraid of the bear. The bears. The bears are group 1 and 2 metals and polyatomic ions. Okay? So, if you have a group 1 and 2 metal or a polyatomic ion, the bears, the chihuahua won't attack the bear unless it absolutely has to and has nothing else to eat. If water's present with those, it's like going to take the safe route and it's going to attack the water. Okay? If all that is a bear, I mean the chihuahua's going to die anyway, so he's got to try. He's going to attack the bear. Okay? Up there, I have the bear, but that little girl right there, that little angry looking molecule thing, the ugly one, she's scary. She's polyatomic. So that's poly and that's group 1 and 2 metals, but I just call all of them bears. So they're all bears and they're all scary to the chihuahuas. So let's see how that comes into play in our 4 examples. So I'm only going to draw the actual cell one more time because there's not much to it. Because I think we can do these problems where we predict what's produced at the anode and the cathode without drawing it every time. So we've got our plus and minus. Let's actually swap it this time. I'm going to make it minus and plus. Make this minus, make this plus. Minus is the, what's minus? Cathode. Oh, I forgot to tell you the EPA van. Plus is the anode, and then the cathode occurs reduction, and the oxidation occurs at the anode. Now, a quick way to remember the whole signage thing, EPA van. If you don't know the EPA, you can do ape van, the ape van, or the EPA van. Basically what this is saying, electrolytic positive anode, voltaic anode negative. And there's Vanna White. Do y'all still know who Vanna White is? Who is Vanna White? Wheel of Fortune chick. She used to actually have a real job and actually have to turn the letters. Now she just touches them. But back in the day, it was like legit thing on a pole that she had to turn. It was way more entertaining than it is now. But anywho, my saying used to be Vanna White works for the EPA, Vanna, but then it just kind of molded from that to that. I don't know. So either one you use, electrolytic positive anode, voltaic anode negative. Okay? So that'll help keep it straight. Now, in this first sketch, it says molten sodium chloride. What does that mean? Liquid. So what form is it in the vat? Exactly, in ions. We cannot run electricity through a solid crystal. Okay, we have to have free-flowing ions for redox to occur. Now, Na plus Cl minus. Na plus is a group 1 metal. It's a bear, right? But the chihuahuas running through have no choice. They have to oxidize one of those things and they have to reduce the other. There's no options, so they're going to do it because they have to eat. So, rule, the metals are the ones that are always reduced. The nonmetals and the polyatomics are the ones that are oxidized. So, the reduction of Na will give us what? Na plus will give us, reduce Na plus, Na, and so we would have one electron here. That would be what's occurring at the cathode. So if we electrolyze molten sodium chloride, we would make sodium solid. There you go, Rui, there it is. There's the sodium solid at the cathode. This is the primary way that it's produced in industry because sodium is not naturally occurring because it's too reactive. You can't just go mining for sodium. You're not going to find it. So it has to be produced and then stored under oil. And then you can purchase it. Like we have a few chunks here, but we don't keep a lot because we don't trust y'all. So someone would break in. We don't need it at all. just to have because it's cool. Yeah, we really don't. I hope you're not playing with too much gallium there. It's still a heavy metal. So, okay, good. Just checking. All right, so what's oxidized then at the anode? Cl minus, and what does it make when it's oxidized? Cl2. And then we have 2 electrons on the right because we need 2 chlorines. So what is produced at the anode? Chlorine gas. It's a double whammy. We got something that'll explode and something that'll kill you if you breathe. Breathe it. It's awesome. Okay? Now this is molten. This is not going to be something that you're going to be able to do at home. The next one you can do at home, and we'll talk about it. But do y'all have any questions? So the point of this, be able to tell me what's produced at each electrode. So now I'm going to show you how to do it without drawing all this stuff, because you really don't need to draw it all. In part B, in the vat we would have aqueous sodium chloride. So what's floating around in the vat? Water, Na+, and Cl-. Okay, so I'm just going to go oxidation anode here. I'm going to do reduction cathode here. So, what potential 2 things could be reduced? What 2 things have the possibility of being reduced? H2O and Na+. Those 2 things can be reduced. So now the Chihuahua has got some choices. Na+ is a bear. So the Chihuahua's like, heck no, I'm going for the water. The Chihuahua's going to attack the water. So in this case, the water is reduced. So what are my products at the cathode? Reduction makes H2 and it's basic. So those are my products at the cathode. What are my possibilities at the anode? Water and Cl-. Is Cl- a group 1 or 2 metal or a polyatomic ion? Nope, so it's not a bear. So why have water when you could have chloride ions, right? So what are we going to make? Chlorine gas. And I can just balance that one because whatever. All right, so anyway, at the anode then of aqueous sodium chloride, we produce chlorine and then we produce H2 at the other. This you can do at home. Producing chlorine gas, I know it sounds scary, but if you do it just in normal salt water, put some in a small amount of water, it'll kind of smell like a swimming pool, but it's not going to kill you. What are you going to use for your electrodes? Really, not metal. Well, it needs to be an inert metal, so you got to use like titanium. You could use carbon. You could use pencil lead. Some really big pencil leads. Dinosaur bones? I don't know if that'll work. So anyway, yeah. So that's what's produced when you have those things. Now, if you're asked on the AP, why is sodium not reduced? You can't say it's a bear, please. That would be a really bad AP answer. The reason is, and the real way to do this, and this just saves you a lot of time, is to do this appropriately, you would look up the reduction potential for water, you would look up the reduction potential for sodium plus, and whichever is bigger is the one you would take. So you would say water has a higher reduction potential. And why that doesn't sound hard, but why I don't like to do it is when you get to this side. You'd have to look up the reduction potentials because we don't have an oxidation table, and you'd have to choose the one with the lower reduction potential, and that would be the one that would be oxidized. So that just gets a little confusing, okay? So you would just say sodium is more apt to be, water is more apt to be reduced than sodium, and chloride ions are more apt to be oxidized than water, and that's all you'd say, okay? All right, let's do our last 2 examples of this, and we'll get on to the fun physics stuff. All right, aqueous iron 3 sulfate. So we've got aqueous iron 3 sulfate. What's in it? We can do this quickly now. Water and iron 3 and sulfate. So reduction at the cathode. What are the 2 options? Water and iron plus 3. Which one is it? Iron, because iron is not a group 1 or group 2 metal. So we're going to plate iron at the cathode, and then oxidation occurs at the anode. What are our two options? Water or SO4 minus. Who's going to be oxidized? Water. How come? SO4 is a bear, meaning water is more apt to be oxidized than sulfate. So when we oxidize water, we make oxygen, and it's acidic. So we make oxygen gas and H plus at the anode and iron at the cathode. All right, how about the last one? It is sodium sulfate, aqueous sodium sulfate. Aqueous, wow, what do we do here? Yeah, just water. This is a bear, and this is a bear. So water is both reduced and oxidized. So we make oxygen and H plus at the anode, and we make hydrogen and OH minus at the cathode. So electrolyzing water and electrolyzing sodium sulfate solution, same products. Why is my phone blowing up? I am. Everybody wants a piece of me. All right. Moving on. Calculations. Okay, so these are kind of, people are like, why do I need to know all this stuff? This is kind of the practical application to what's going on here. If you were working in industry and you worked in a place that produces copper or copper plates things or whatever, you're going to be doing a lot of work with electrolysis. And in these questions, we're concerned with how much stuff, how many grams, how many liters are we going to produce during this process. So this is meshing our physics and chemistry together pretty intensely. So in this first problem, calculate the mass of copper metal produced during the passage of 2.50 amps of current through a solution of copper 2 sulfate for 50 minutes. So we're running this electrolytic cell. We know the amperage. It's going for 50 minutes. How much copper are we going to make? We're starting with what in our vat? What's in our vat? It's in the problem, copper 2 sulfate. Okay? So before you can do any problem when we have electrolysis, I need a balanced half reaction because we have to know the number of moles associated with the transfer. So we're starting with copper 2. And what are we making? We're making copper. So there's my balanced half reaction. Doing this now, I can do this problem pretty easy. One other thing I need you to know to be successful with this is what an amp is, and you should know that from physics. What is an amp? Coulomb per second. So if you ever see an amp, immediately change it to coulomb per second, because that's going to be more useful to us. All right, so we're going to do a really long dimensional analysis problem, and we're going to start with one of our givens. I always start with the given with the easiest, less complex unit, which would be minutes or coulombs per second? Minutes. So I'm going to start with 50 minutes. What do you think I'm going to convert those minutes to be at all useful? Seconds. So we've got 60 seconds per minute. All right. Now I got to get into some sort of relationship. What can I do?
Oh, you can put like 2.5 coulombs.
Exactly. I'm going to put 2.50 coulombs per second. That's awesome. So just being honest, I'm really uncomfortable in physics world. Not happy here. I want to get back to chemistry world. Get me back there, somebody. I like how y'all are just rude. Yes. But no, but that's not what I would put in there. I won't write Faraday in there. And you said 1 coulomb, which isn't right either, so neither one of you were right. Yes, 96,500 coulombs is the charge of 1 mole of electrons. 96,500 coulombs is the charge of 1 mole of electrons. So the coulombs cancel. Now I'm in a place I'm a little more comfortable with. Remember, we're going to how many grams we're producing of this copper. Does anyone see a connection between moles of electron and that copper? Oh my gosh, Rui's actually he's getting into this stuff. So, for every, say that again.
This is this is really cool.
Somebody appreciates it. All right, so we have 2 moles of electrons for every 1 mole of copper. So now I'm in moles of copper. How do I get to grams of copper? For every 1 mole of copper, I have 63.55 grams. All right. So to 2 sigafigs, how many grams do I have? I meant 3. I literally meant 3, and 2 came out of my mouth. Like, that's insane. What? Rain Man, what is it? 2.47. You're off by 10. Considering it's only 2 grams, 10 is a lot. All right. So if I were an industrial dude, and I'm like, I could be an industrial gal too. If I were an industrial person and I needed at least 3 grams for every one of my earrings, what should I do? What could I do? Increase the amps? Run it longer? That would be about it. Those are your 2 options. That's it. Okay, so now, this is only reduction, right? Remember, oxidation has to be going on at the same time. So the next question is asking, in the same situation, what volume of oxygen measured at STP is produced by the oxidation of water that occurs concurrently with the above reaction? Why is water being oxidized? Because remember, it was copper 2 sulfate that was in the thing, and this guy is a bear. So water is going to be done. We're going to set everything up the same except that last bit. So what do you think we need to figure out our ratios of moles of electrons and such? Balanced half reaction is important. So water being oxidized, I'm just wanting you to get used to writing this. If we're oxidizing water, we make oxygen, and it's acidic. And to balance it, I need 2 of those, 4 of those, and 4 electrons. So that is absolutely balanced. So go ahead and set yours up, starting with the same time. Is it the same time? Yes. Concurrently with the above problem. Just making sure my mic was still on. All right. So again, it's our 50 minutes for there are 60 seconds for every 1 minute. So you guys go ahead and write it down now that you know how to do these, and I will quietly write the answer here. Is it 3 amps? I don't even remember. Okay, we are looking for liters of oxygen. Because it's at STP, yeah, that's right, 0.435. If you would have done it without the calculator, I would have been a little more impressed. Okay. All right. So set up the same, but because we're at STP, we can use 22.4 moles per liter to solve. What happens if this weren't an STP, though? What if I were to say this happened at 270 K and 2 ATM? What would you do differently? What about gas? What? I want specific. What would we do? The ideal gas law. What would we do with that? They give us temperature. They give us, you calculate the number of moles. How? Right, so we stop here, right? We'd plug that into there, Plug in the R, we know the T, solve for the volume. Okay? We can only do 22.4 because they said STP. All right, our last problem. This one, I'm going to see smarty pantses. This is a challenge. Challenging you guys. No, it's challenging enough without a calculator. This is the sexy problem of the unit. This is it. An aqueous solution of an unknown salt of chromium is electrolyzed by a current of 3 amps for an hour. The process produces 1.94 grams of chromium metal at the cathode. What is the oxidation state of the chromium? So this is the only thing I'm going to give you, and then you're going to have to talk to me. This is going to be really boring for people at home because they probably won't be able to hear you. But that's what we need, right? So how many electrons do I add to that? And what is that going to make? Chromium. So keeping that in mind, give me some ideas of things we can do. Solve for what? The number of electrons? I'm game. Let's solve for moles of electrons. How do I do that? 1 hour, which is 3,600 seconds, right? Okay. So then what can I do to get moles of electrons? Because that's what I'm doing right now, because that's what Noah wants us to do. What can we do? 3 coulombs per second. We got an amp right there. So 3 coulombs per second. And then? Good. 1 mole of electrons. So there it is. There's moles of electrons, right? We can't take it anywhere else, can we? Because we don't know the ratio. So we have to stop here. What is it? It's a small number. Thanks. Thanks for that. What is the number? 112 moles of electrons. All right. What else can we find that would be useful? So what can we get from grams of chromium metal? Okay, let's just get moles of chromium metal. No, it's not that hard. It's not that hard, but there's a little trick. So we're going to figure out moles of chromium. I'm good with that too. Moles of chromium. 0.0373? I need it to be correct or this won't work. What's the molar mass of chromium? 0.037, is that what you said? I need a second on that because Noah's not very convincing. All right. Interesting. Look at the balanced equation. We're looking for this, right? We know this, and we know that. We just calculated those things.
Yes, you divide like 0.112 moles of electrons by 0.037 moles of chromium. You get like 2.999, just like 3.
It's the ratio. Look at this. This is really cool. Isn't X equal to the moles of electron over the moles of chromium? Isn't that equal to X? X over 1 is X. Well, we just don't have a 1 on the bottom, but we know moles of electrons. We know moles of chromium. We can figure it out. So as Rui said, take your moles of electrons divided by, did somebody fall out of their chair? From a sneeze, people at home. All right, so this is really, really close to 3. So our answer is +3. And that, my friends, is a sexy problem. Okay, so I won't be here tomorrow. A lot of you won't. If you're not here tomorrow, group quiz grades are no counts. You'll get a blank copy that you can have on Monday to use to study for the test on Tuesday. Okay? Monday will be extra credit. Okay? All right.